All right, this problem is another work problem. It reads, an aquarium 2 meters long, 1 meter wide, and 1 meter deep is full of water. So there's the dimensions right there. Find the work needed to pump half of the water out of the aquarium. All right, so we need to pump from, you can think of it as from, even though this is 1 right here, we're going to go from 0 to 1/2. Right, let me write this over here. So we're going to go from 0 to 1/2 a meter. Okay, so the general work formula is work equals the integral from a to b of force times distance. In this problem, it's going to be from 0 to 1/2. So first we want to make a little rectangular slice in our tank, and you want to think of the rectangular slice like this. And we know that this distance back here, I didn't really draw this to scale, not that it matters. All right. We know that this is 2 meters. So I'm drawing my little red tank, right? My little red slice right here. We know that this is 1 meter, and we're going to say that the thickness of our slice is dx. Okay, so it's a tiny thickness, dx. Okay, so this is dx. All right, so the volume of our slice is 2 length times width times height. So 2 times 1 dx, or 2 dx. Okay. Next, so we found the volume of the slice. Next step, we're going to multiply the volume by 9.8 times 1,000. This is gravity, acceleration due to gravity. This is the density of water, which is right here. And that's the little trick that you do to get the force of the slice. Because we know that our volume that we got above, right here, that the unit of volume is going to be in meters cubed, right? So meters times meters times meters. So it's going to be meters cubed. So let's just pretend we had like a meters cubed right here, right? So if we're multiplying meters cubed by, I think about this for a second. Yeah, by all this stuff right here, this meters cubed would wipe out with this meter cube right there. Then you're left with meters times kilograms over second squared. And if you look over here, meters times kilogram over second squared. That's a Newton, which is a unit of force. So that's how you take care of that. All right, so we're going to do that. Multiply our volume with our tiny thickness, which is made up of our tiny thickness, times the 9.8 times 1,000. We do that, and we get this right here, which is 19,600 dx. All right, then we calculate our generic displacement. So like how much that rectangular slice that we figured out, how much it's going to move. Well, we're going to just say it moves by x. All right, so, and then when we set our boundaries, we're going to say that it goes from 0, we're going to say it goes from 0 to, that's kind of weird writing it backwards like this, but it's going to go from 0 to 1/2. Okay, wait, that is totally, well, I guess we could do it like, I guess we could write it like this. From 0 to 1/2. But it's going to basically just go, so take up all that right there. All right, so the generic displacement is x. All right, so because it travels x units, and specifically for this problem, when you do our boundaries, we're going to end up doing 0 to 1/2. All right, so then we set up our boundaries, 0 to 1/2. We put in this equation right here, integrate it, And that's it. There's a 0 down here. Oops. There's a 0 down here. And so the second part's easy. It ends up being in joules. Wait, don't look at that now. That's the wrong answer right there. You shouldn't see that. I'll have to delete that one. The right answer is right here. I got the other answer before because I forgot to do 0 to 1/2. So it's important that you go from 0 to 1/2, not to 1. And that's it. That's the work required to pump half the water out.